Hi, this is week 30 of AP Physics, and we're starting Unit 9, which deals with DC circuits. For our agenda, we're going to be looking at electric current as well as resistivity. And for our lesson objectives, the students will learn what are the components of a circuit as well as which factors affect the current in a circuit. Let's go ahead and get started.
Let's begin our lesson on electric current. What exactly is a current? The current is the rate at which charge flows through a surface. The average current is the amount of charge, which is denoted by the symbol delta Q, that flows through the area, whose symbol is A, in a time interval, delta T, while perpendicular to that area. The SI unit for the current is coulombs per second. That is also known as the ampere, whose symbol for ampere is A. The average current is found with the equation I is equal to delta Q over delta T, where delta Q is the charge and delta T is time. When charge flows through a surface, they can be either positive, negative, or both. The direction of the conventional current is in the direction of the flow of the positive charges. Moving charges, whether positive or negative, are referred to as charge carriers. When the current is steady, the average current and instantaneous current are the same. Instantaneous current is the time of the average current as the time interval approaches zero, as shown in the formulas below.
Next, let's go ahead and take a look at some examples. In example 1, we're asked the following. It says, the amount of charge that passes through a filament of a certain light bulb in 2 seconds is 1.67 coulombs. In part A, they ask you to find the average current of the light bulb. So let's go ahead and do that. So for our current, average current is going to be the charge over the amount of time. So for our charge is 1.67 coulombs, and the time, it was 2 seconds. So we're just going to go ahead and plug it into our calculator, divide both of those numbers, and we'll get our answer. So it is 0.835 amperes. So that's part A. In part B, now we're asked also find the number of electrons that pass through the filament in 5 seconds, and given to us at the bottom is that the charge of one electron is 1.6 times 10 to the negative 19 coulombs. Alright, so 5 seconds, that's what we have. So for our time is 5 seconds. And how much charge will we get in 5 seconds? Well, we have the amperage, which is 0.8835 amperes, which is coulombs per second. So I'm going to go ahead and use that. 0.835 coulombs per second. That's what an ampere is. So I'm going to multiply both of these numbers. So we're going to get 4.175 coulombs. So that's a charge. So how many electrons is that? Well, we know one electron has a charge of 1.6 times 10 to the negative 19 coulombs. So we're going to use that number along with this one. So we're going to set it up here. We're going to say one electron has a charge of 1.6 times 10 to the negative 19 coulombs. Okay, so that's going to go ahead and be our setup. So divided by 1.6 times 10 to the negative 19 gives us, we're going to round it up slightly, 2.61 times 10 to the 19 electrons. And that's how many electrons will go through the filament in 5 seconds. That is example 1. Next, let's go ahead and move along to problem number 1. It said, is it possible to have an instantaneous current of E/half of an electron? Alright, is that possible? And the answer is yes, it is possible if you have one electron every 2 seconds. So that will give you that current. Alright, let's go ahead and solve problem number 2. In problem number 2, you ask the following. It says, a 9-volt battery delivers a current of 1.34 amperes to a light bulb filament of a pocket flashlight. In part A, how much charge passes through the filament in 2 seconds? Alright, so we're going to go ahead and take a look at our same equation again. So now they're asking you for the charge. We have the current and they give you the charge. So we're going to go ahead and rearrange it. So we're going to multiply both sides by time. So we end up with this. Q is equal to the average current multiplied times the time. And that's going to be our answer for part A. So how much charge passes is the current times the time. So now let's go ahead and plug those guys in. It is 1.34 for the current amperes multiplied times the time, and it is 2 minutes. Now 2 minutes Remember that the amperes is coulombs per second. So we actually need seconds. So 2 minutes is equivalent to 120 seconds. All right, all we got to do now is just go ahead and multiply and we get our answer of, I'm going to round it off slightly to 161 coulombs. That would be our answer for the part A. In part B, they ask you how many electrons pass through the filament in that amount of time. So again, we're going to go ahead and use our charge, 161 coulombs. This is for part B. And they want to know how many electrons is that? Well, I know that every one electron has a charge of 1.6 times 10 to the negative 19 coulombs. So we're going to go ahead and divide 161 divided by 1.6 times 10 to the negative 19. It's going to go ahead and give us roughly, we're going to round it off to 1.0 times 10 to the 21 electrons that will go through the filament in that time interval of 2 minutes. Alright, that takes care of problem number 2. In problem number 3, we ask the following question. It says, consider positive and negative charges all moving horizontally with the same speed through 4 regions in figure. So we have A, B, C, D. Rank the magnitudes of the currents from lowest to highest. And we are given, here are our options. I, of course, is a current, and they give us all of those. All right, to solve the problem from lowest to highest, what you want to go ahead and do is you want to count all the charges. Does not matter positive or negative, just count all the charges. So which one's got the lowest charge out of all of them? So that'll be this one, letter D. All right, so we can narrow down our answers. You're going to be A or B. Who's got the next lowest? That'll be B here with only 3. Then the next one will be C. And then the last one will be A with 5. So the answer for this question will be letter D. So it is from lowest to highest, D, B, C, A. And that is how you solve this problem.
Next, let's go on and talk about resistivity. The word circuit means a closed loop around which current can circulate. What about a short circuit? A short circuit occurs when an element with lower resistance diverts current away from the components. In a circuit, the battery pumps charge through the bulb and around the loop. Now here we have a picture on the left of a setup and a diagram for that same setup. So let's begin with the battery here. So for the battery, we're going to go ahead and have 2 AA batteries here, and they're going to be shown in the diagram as 2 parallel lines, with the longer line being the positive side of the battery. And that's going to go ahead and create a current going through the wire into the bulb. And here is the symbol for the bulb in the diagram. Next, to measure the voltage, we're going to go ahead and use a voltmeter here, connected to one side of the bulb and the other. And here's the voltmeter on the schematic. And finally, to measure the current, we can use an ammeter here. And here's your diagram. Of course, a multimeter can work as both a voltmeter and an ammeter. Now, an ammeter is used to measure the current I in the bulb. The voltmeter measures the potential difference of voltage, delta V, between the 2 ends of the filament. The current in a conductor is proportional to the applied voltage. So a higher voltage will give you a higher current and vice versa. The ratio of voltage across a conductor to the current is known as the resistance. The resistance is the voltage over the current. So the SI unit of resistance is volts per ampere, also known as the ohms. And the symbol for ohms is Greek letter omega. Ohm's law states that electric current is proportional to voltage and inversely proportional to resistance. So therefore, as the voltage increases, the current will also increase. But as the resistance increases, since it's inversely proportional to current, the current will decrease. A resistor is a conductor that provides a specific resistance in an electric current. Perhaps you want a particular current. Too high might be too much for the particular device. So you want a conductor or a resistor that will give you the particular current that you're looking for. Now, not all materials follow Ohm's law. Those that do are known as ohmic materials, and those that do not are called non-ohmic materials. In the graph, you would see in part A of straight slope That will be for a material that follows Ohm's law. But at higher current, some materials do not follow Ohm's law. So what you get is, as the current increases, you're going to go ahead and get the curved line diverting away, therefore giving you different properties away from Ohm's law. For ohmic materials, the resistance remains constant over different voltages. For non-ohmic materials, the resistance changes with the voltage. A diode is a non-ohmic element that acts like a one-way valve for currents, so therefore the current can only flow in one direction. That's what a diode is. The resistance of an ohmic conductor increases with length and also a smaller cross-sectional area. So therefore, it is proportional to the length. So the longer the length, the higher the resistance, and inversely proportional to the area. So the smaller the area, the higher the resistance as well. So here, resistivity is denoted by this letter right here. Looks like a P. The resistivity is also affected by temperature. Now, on this table right here, we have the different materials plus their resistivity along with the temperature. So for silver, copper, gold, and aluminum, as well as the rest of them, here's the resistivity in ohms times meter at this particular temperature. Now let's go ahead and take a look at some examples.
Next, let's take a look at example 2. Here we ask the following. It says calculate the resistance per unit length of a 22 gauge nichrome wire of radius 0.321 millimeters. Alright, so first of all, wanted to point out that the radius is in millimeters. And for the formula, we're going to need the area. Alright, so formula for area is going to be pi r squared. So first of all, our radius has to be in meters. So to change it from meters to millimeters, we're going to divide it by 1,000. So our radius is this 0.000321 meters. Now we have that, we can substitute it into the formula to get the area. So our area is equal to pi multiplied times the r, 0.000321 meters, and that is square. And let's get our answer. So plug it into the calculator. Square times pi gives us 3.23 times 10 to the negative 7 meters squared. That is our area. Now looking back at the question, they want resistance per unit length. So we're going to modify this formula a little bit. It'll be this, R over L is equal to, symbol it looks like a P, is actually lowercase Greek letter R, which is pronounced rho, and that's our resistivity, divided by A, which is the area here we have. Okay, so I'm going to go ahead and substitute the area. And the resistivity is going to go ahead and be on our chart on the previous table. Alright, so here we go. There it is, 150 times 10 to the negative 8 ohms per meter. Ohms times meters, pardon me. And so now all we got to go ahead and do is divide both of these numbers, and we're going to go ahead and get our answer. And comes out to be 4.63 ohms per meter. That is our answer. That's our symbol for ohms. Alright, so that is part 1 of example 2. Next, let's take a look at part B of example 2. Here we ask the following. If a potential difference of 10 volts is maintained across a 1 meter length of the nichrome wire, what is the current in the wire? Alright, so here we got our two formulas that have resistance, and the second formula has our current, which is potential difference over the current. So now, since they're both equal resistance, we can equal them out to each other. So it's going to go ahead and look like this. I is equal to resistivity, which is rho, times length over area. Alright, so now we have that. We want to go ahead and isolate the I. So we're going to go ahead and cross multiply a little bit. So it's going to be V, the voltage times the area. It's equal to I multiplied times resistivity times the length. Then I'm going to go ahead and divide both sides by resistivity and length. So we're going to end up with the formula for I, which is the current. Alright, so it's going to be voltage over area divided by resistivity times the length, which is 1 meter. Alright, so let's go ahead and start plugging in all the values. 10 volts, the area, we have to solve for it in part A. it is 3.23 times 10 to the negative 7 meters squared over the resistivity. We looked it up in the table. For this wire, it's 150 times 10 to the negative 8 ohms times meter multiplied times the length. They let us know that it was a 1 meter. That was the length of the wire. So once you plug it all in, we'll be able to figure out the current going through the wire. So it's going to go ahead and be 10 times 3 times 10, 3.23 times 10 to the negative 7 divided by 150 times 10 to the negative 8 times 1. Alright, so that's going to go ahead and give me an answer of 2.15 amperes. Alright, so that is the current in our wire. Next, let's go ahead and take a look at part C of example 2. Here they ask us the wire is melted down and recast with a length that is twice that of the original. Find the new resistance Rn as a multiple of the old resistance Ro. Alright, so let's go ahead and do this problem. First of all, in this problem now we have twice the length, so that's going to go ahead and change the area. Now what does not change between these two will be the volume. So the volume of the old wire is equal to the volume of the new wire. Even though it's melted and reshaped, still the same volume. Alright, so volume for a wire, which is essentially a cylinder, will be the area multiplied times the length. So the old area multiplied times the old length is equal to the new area multiplied times the new length. So if I want the new area for this brand new wire, I'm going to go ahead and divide by Ln on both sides. And that's going to give me the new area for this wire that's been stretched out to twice the length. So it's going to go ahead and be as follows. The old area was 3.23 times 10 to the negative 7 meters squared multiplied times 1 meter divided by the new length, which is twice as long, which is 2 meters. So that's going to go ahead and give us an answer of 3.23 times 10 to the negative 7 divided by 2, 1.62, I guess we can run that off, or let's keep all the digits, times 10 to the negative 7 meters squared. Alright, so that is our new area, 1.615 times 10 to the negative 5 meters squared. Alright, so now that we have that, let's figure out the resistance before and the resistance after, and then we can go ahead and compare them to each other. Alright, so our original resistance was the resistivity, which is 150 times 10 to the negative 8 ohms times meters, multiplied times the length, which is just 1 meter, divided by the area, the old area, 3.23 times 10 to the negative 7 meters squared. Alright, for the new resistance, it's going to go ahead and be 150 times 10 to the negative 8. This remains the same. The new length is 2 meters, and the new area becomes 1.615 times 10 to the negative 7 meters squared. So now we're going to go ahead and solve for both of these and compare them to each other and see how they differ. So it's going to go ahead and give us 4.64. For the new resistance, it's going to be 150 times 10 to the negative 8 multiplied times 2 divided by 1.615 times 10 to the negative 7 gives us our answer of 18.58. So now let's go ahead and compare them to each other. So I'm just going to go ahead and divide them. 18.58 over 4.64, and our answer comes out to be roughly 4. Alright, so what does that mean? It means our new resistance is 4 times bigger than the original one. So I'm going to write Rn is equal to 4 times Ro. So that will be the answer for part C of example 2. In problem 4, we ask the following question. Would replacing the nichrome wire with a copper wire result in a higher or lower current? Alright, so first of all, the values for the resistivity of these two wires, nichrome wire is 150 times 10 to the 8 versus copper has a much lower resistivity of 1.7 times 10 to the 8. Now notice how resistivity and resistance are proportional to each other, so therefore for the copper, a lower resistivity will give you a lower resistance. And resistance is inversely proportional to current. So therefore, lower resistance will give you a higher current. So the answer for this question, replacing the wire with copper, will give you a higher current. There you go. In problem 5, we're asked the following question. What is the resistance of a 6 meter length of nichrome wire that has a radius of 0.321 millimeters? Alright, so this number, we've used it before, that radius. So we know the area to be 3.23 times 10 to the negative 7 meters squared. We also know the nichrome wire has a resistivity of 150 times 10 to the negative 8 ohms times meters. So all we got to do to find the resistance is go ahead and plug them in. We have the new length of 6 meters, and that's going to go ahead and give us our answer. So it would be 150 times 10 to the negative 8 multiplied times the length of this wire, which is 6 meters long, divided by the area, which is 3.23 times 10 to negative 7 meters squared. So we go ahead and we plug all of those values into our calculator and see what we get. We're going to end up with 27.9 ohms of resistance. That's part 1. Part 2, they ask you, how much current does it carry when connected to a 120 volt source? Alright, so we know that resistance is the potential difference over the current. So we're going to go ahead and multiply this because we want to solve for the current. It's going to go ahead and be potential difference over the resistance. So we have a source of 120 volts divided by a resistance of 27.9 ohms. So that's going to go ahead and give us 4.3 amps. That is the second part of problem 5. This brings us to the end of this week's lesson. Thank you so much for watching.